be the last technical session. Can you believe it? The 2 days are coming to an end almost. Let's have a huge round of applause for the audience who are still there and all ears to listen in to the last technical session. And at the same time, I would like to welcome our final speaker. Sir is already here, Mr. Avinash Khare, industry consultant and trainer. With a huge round of applause, his topic for the technical session is challenges in manufacturing of large size stamping dies. Huge round of applause for sir.
So, ladies and gentlemen, am I audible? I suppose, yeah. Because it's a challenge for me to ignite some attention in you people, being the very last session, for discussing the challenges in manufacturing for large size stamping dies. My introduction says that I am industry consultant, but before that I have been working for Tata Motors tool room for past 33 years. I have been head of die design. I have been an electronics engineer. I have been indulging into electronics R&D as well, and I have been a teacher in Pune University as well. And now I am also working for IMTMA, and I do some of their courses on sheet metal forming, basic and advanced courses, etc. So that's my brief background. Well, my presentation is packed with lot of information, and there is very limited time. So let me throw some ideas and some hints of what the solutions could look like. Okay. Without much ado, what do we mean by large size stamping dies? It is shown in the picture over there. So it is something like a die weighing 20 tons, a die measuring 4.5 meter by 2.5 meter. Okay, that is the casting size. So we are talking of really huge dimensions, and you would appreciate that for machining this kind of big mass of steel, you require obviously a machine which is bigger than this. So possibly you will have maybe a bridge type portal machine with 6 meter table and with 3 meter y axis and about 2 meter, 2.5 meter z axis. Now if we are talking of this size of things, sorry, I forgot to mention the agenda. The questions that we are addressing today is why large size dies almost never finish first shot okay. We always say that die making is art of inaccuracy, because something you produce, then you keep on struggling. So all your plan or your timelines and all your Gantt chart go for a toss. The moment it comes in tryout and assembly, all your timelines go for a toss. That is a fact of life. Okay. So we will be dwelling in some of the reasons why this happens and how to overcome, partly, not wholly, but partly how you can overcome some of these problems. Then what makes the dies so much heavier to handle? Can it not be made lighter? And what are the ways and means of making dies little bit lighter? I mean, okay, there is a physical limit to how much lighter we can make it. The third is, why dies require so much of handwork despite having best of the technology in CNC machines and best brands of imported German, Japanese machines. Still we end up doing lot of handwork in the die. We say that die to haath ki safai se banta hai. CNC does just a preparatory work, and designer, I mean, they say that designer is only initial proposition maker of how die should be started, but finally die is made the hard way in shop floor, and that I have witnessed for several years. Okay. Then fourth question is, why we do so much of simulation, okay, but still we find that the simulation predicts something and what we get is something else. Simulation is something that I love to call as techno-astrology. Now, while we do techno-astrology, we forget to consider the prabhav of Shani, Rahu, Ketu, because we in simulation concentrate only on the CAD model of the surface, and we take die surfaces parallel to the job surface. We do not consider the variations in presses, we do not consider the deflections in dies and so on. So many things we do not consider. Even scrap flow we do not consider for that matter. So many things we do not consider while doing techno-astrology. That is why it does not match, but we will see some of these things. Then lastly, Industry 4 is the buzzword. Industry 4 is omnipresent. It is there everywhere. So, what Industry 4 compatibility features could be there in stamping dies? Now, these are the 5 things that I would like to broach in my talk. Only 5. Okay, time is limited. I can go on and on because I teach 2 days, 3 days course also on the same subjects, but okay. Now, why are large dies almost never first shot okay upon manufacturing? The problem is, for making a good die set, the upper die surface and lower die surface, the upper die trimline profile and the lower die profile has to match within 10 to 20 microns. Now, imagine for this size of dies, matching in 10 to 20 micron is a very, very tall order, and die is a mass of steel, isn't it? We agree, it is a mass of steel, and so is a machine is a bigger mass of steel, being a bigger mass of steel. Now, what is the thermal coefficient of steel, sir? The thermal coefficient of steel is that it expands by 10 micron per meter per degree, right? And how much temperature swing we have in 24 hours in our cities, in our factory? Factories are certainly not AC, they are not meant to be AC, and they should not be AC, according to me. That will create more problem than what it will solve. So, if 15 degrees is the temperature variation in 24 hours, if you are going to take more than 24 hours while doing finishing cut with ball nose cutter, your scan will be more, you can't interrupt. So, your machining will go on and on for more than 24 hours at a stretch. Your casting will breathe by 0.4 to 0.5 mm, sir. So, where is 10 micron? Where is 20 micron? You can never achieve that, take it from me. It is physics. It is plain and simple physics. Though we don't realize it, we don't acknowledge it. And if you don't believe me, you can do one test on your machine. Just put a dial on your CNC machine. Just take, so that the coordinate readings shown are same, and you put dial and you take reading after every 1 hour for 24 hours. You can see your machine is also breathing by 0.4, 0.5 mm. So, if your job is breathing, if your machine is breathing by 0.4, 0.5 mm, how can you get 10 to 20 micron matching, sir? You can't. Not only on machining you cannot get matching, even inspection you can't do with that precision. Best of CMM will guarantee you in this particular measuring volume an accuracy of 120 microns, sir. And any digitization based on light, it will have accuracy of 50 microns. So, 10 micron you can't even measure. Okay. So, the thing is, you end up with a situation that you have upper die, lower die, both are machined on a CNC machine, best possible CNC machine, but you don't know which one is right. Which one is closer to the CAD model, you can't figure out. So, what do? We say upar wala is always right. So, you take it as a master, take it in spotting press, glue lagaiye, and then haath ki safai. Grind the lower die to suit with the upper die. That's what we do. That is what I mean by art of inaccuracy, and that is what I mean ki die to haath ki safai se banti hai. Okay? I think big die makers would agree with me. They would have experienced it a lot. Okay? Now, this is just what I have spoken, so it's fine. Okay? So 10 micron we cannot get, and we can't even measure also. So, forget that. And in our machine what happens? Suppose you have a bridge type machine and your temperature goes up by 10 degrees. What will happen? Your 2 columns on the right side figure I am showing, the 2 columns will become taller by some amount. Your spindle will become longer by some amount. Fine, you can always adjust by giving Z offset. But what will happen when your cross beam will expand? When your cross beam will expand, your structure will distort, and then it will lose orthogonality also, because your cross beam will become like a banana. One day it will become like seedha banana, one day it will become like ulta banana, one day it will lean forward, one day it will be in 45 degrees plane. So, every day the behavior will be non-repetitive. It is not something that you can determine the error and compensate, because every day the machine will distort in a different way. It will choose to distort in a different way. Okay. What do? So, that's a problem. That's a problem. and it is physics. You buy the best machine, it will happen. You can't defeat thermal expansion. You can go for thermosymmetric design, but that will make the machine too delicate, and then it will vibrate a lot while taking heavy cut. Okay. And besides, there are several sources of error. I will not leave, they are put in that yellow pad. So, there are so many sources in such big machine to give you error, and even if you go for a different morphology of the machine, it will have some other problem. It will have the effect of moving CG, it will have effect of sag, will have the sagging when the spindle comes out in case of HBM kind of design. So, all kind of machine design will have some or the other problem, but none of these, believe me, will give you accuracy of 10 to 20 micron matching that you are looking for. So, what do you do is, and why the requirement is 10 to 20 micron? By the way, this is the trim line shown in the figure there, that is the trim line of cutting steel. Now, let us say the trim line is measuring, let us say 4 meter by 2 meter, just for sake of approximation. Now, if you have a sheet thickness of 0.6 mm or 0.8 mm, the cutting clearance required in a cutting die is 10% of sheet thickness. So, you are looking for a uniform thickness of 40 micron or 60 micron. So, plus minus 10 micron is all you can afford, otherwise it will give you severe burrs on cutting. So, that is why I said that 10 to 20 micron matching is required, and requirement is not a fancy, it is a requirement. Okay. So, we take upper die as master and do hath ki safai, and lower die is always easier to grind anyway, because upper die, if you grind, the muck will go in somebody's eye, and it is most unergonomic thing to work like this. So, you would rather, you can grind easily the lower die, but in UK people are crazy. All over the world it is a different hand drive in UK and we follow UK. So, in this matter also we should follow UK. Now, UK people take the lower die as a master and they grind the upper die. You can guess the reason. The reason is very simple. Where is the punch? The punch is on lower die. Something which is having punch is more critical from quality point of view for the stamped part. So, actually where the punch is, that should be taken as master and the other half should be matched, right. So, that is what they choose to do, but then they end up in a situation that they have to handwork on the upper die. Then what do they do? Okay. Then they have to use some spotting presses with features like this one, where you are able to tilt both the upper and lower die, bring them to comfortable ergonomic height. Actually, we do not care about ergonomics while making tool. I can see our tool makers climbing like monkeys on dies and working in most unergonomic postures, okay, which pains me a lot personally. So, features like this in our spotting presses are absolutely required if we want to go the UK way. That is, if we want to take the lower die as master and shoot the upper to the lower one. Otherwise, we can keep doing a mix. Okay. So, that is the one. Now, I spoke about variation, the problems in matching of upper and lower die surfaces in 10 to 20 micron. A shortcut that I propose, and we have followed it also, is that suppose you have a big draw die with a big surface. First of all, you take a reference groove. You cut a reference groove all around. Because the reference groove can be cut within half an hour, you assume that thermal variation will not be so much. So, you will get a relatively more accurate, precise reference groove. Then, while machining rest of the area, while finishing rest of the area, you match the depth to the reference groove. Now, that is the trick of the trade, that is what we say that skill is absolutely required. So, that is a part of skill and learning. Okay. How to manage with the inaccuracies that we have at hand. That is why we call it art of inaccuracy. How to play with inaccuracy and still manage. Now, coming to further part of proving of the die. Now, you can have two situations. One situation is that you have a die where the table is deflecting, but the die is not deflecting. Because a press table is just a slab, there is nothing underneath, there can't be because there is a cushion pad. Okay. So, when all the rated tonnage comes, the table has to flex. Now, when the table flexes and die does not flex, then you see air gap. Okay, you can put a feeler under the die. Okay. Now, what happens in that situation? Okay, nothing much can happen. Only thing that is seen to happen is after every stroke, maybe your die will keep on shifting little bit. So, if it is a cutting die, first part will be okay, in 20th part it will be a disaster, and 50th part maybe the die will get damaged. Okay. So, what do? We say we make tenon slots below the die, so that die cannot move. You key the die to the table, fine, or you make the die very thick so that it will bend along with the table, or you make the die slightly flimsy so that it will bend along with the table, right. These are the approaches done. Now, Fraunhofer Institute Germany recommend that we make the blank holder a little bit flimsy. We do not make it over designed, so that it is able to deflect with the die and with the plate of the press. Okay. And it takes the shape, and under that condition with that deflection you do bedding in tryout, so that whatever quality you prove of that die is assuming that that deflection is there. But then you need a tryout press which is identical to the production press. Otherwise, you have to redo the bedding in HLTO in the production line on the production press. Now, what Japanese do is, now in one case where we have talked of tenon slots, I have faced one more problem, that when the RAM goes up, sometimes the lower die also starts going up along with the upper die, and then after going about 6 inches it drops down. Now, that is positively dangerous, some accident can happen, somebody's feet can go under the table. So, be careful of that. Normally, we do not nowadays give tenon slot, we give conical location on the die or hemispherical location below the die, so that the die can be loaded very fast, it gets self aligned, but it has the flexibility, it does not get lifted when the RAM goes up. Okay. So, it has some flexibility also there, right. Fine. Now, Japanese and German approach of making die and trying out die is different. What Japanese choose to do is, Japanese OEM, most of them have their own tool rooms, and they have a tryout center kind of concept, where they have a single tryout press, as you can see in the middle here. Now, this is exactly same as the lead press on their press line. Okay. So, it has the same deflection characteristics of the table, it has the same cutting velocity, coming down with descending velocity, it has the same kind of wind gathering in the upper die. So, all the characteristic, all the behavior is exactly emulated from the production press, and then they have multiple what they call as die setters or die splitters. Those are like spotting presses which I showed you, where you are able to open the die and hand work on the die. So, simultaneously you are able to work on 8 dies for a single tryout press. Now, this concept is called as tryout center, where you are assuming that you have the tryout press which is exactly replica of production line press, so that you do not have to go to production line and keep it down for doing tryout or doing bedding, right. This is the physical picture of such a tryout center. But what Europeans do is this, what Germans would do is this. Now, tool room people, how many different production line lead presses you can match? I mean, you can't have so many tryout presses obviously. So, you can have a press which is like a mimicry artist. It can mimic Amitabh Bachchan, it can mimic Rajesh Khanna, it can mimic Lata Mangeshkar also if it comes. It can do mimicry of anybody. So, this is the press which when I was in Tata Motors I bought one. This is a hydraulic press which can emulate, you can program the behavior of production press. So, while tryout it will emulate the behavior of that production press, right. So, that is the German approach to doing tryout. Okay. Now, you can see this is a picture of a sheet part which is stamped. You can see so many patterns, and we have found out that these patterns are nothing but the cutter passes of roughing the die. Now what happens when you use big scooping cutters for high productivity? Okay, they generate bands of different hardness on the die. And then what happens that you may mirror finish the die. It will look absolutely good. But when you do, let us say, die with full bottoming, you do embossing or you do crash forming, then those patterns of hardness are seen on the job. Because somewhere your die is harder, somewhere it is lesser harder. And I remember my IIT friend was talking about welding of die. Welding of die is strict no-no, because you can see the weld marks on the part later, because welding is much harder than the substrate. So unless you redo the hardness with laser hardening and match up the hardness of the complete die surfaces, you will see those marks on the part. Okay. So that's the problem. Okay. So uneven hardness on matching surfaces lead to visible marks on the part. Die may look absolutely beautiful, but part will not look. Okay. So another approach is, of course, to do laser hardening, which is a technology which we have bought in Tata Motors and we used to do. Now this gave better result because while doing laser hardening, it has a thermal sensor, it has a radiation pyrometer. So it knows where the rib is behind. So heating has to be modulated according to the mass which is available for cooling, because it is ultimately self-quenching. So indirectly you have to sense where how much attached mass is there for quenching, and accordingly you have to modulate the laser power. Now if you do hardening with that strategy, then you will get uniform hardness, and then this pattern will not be seen. That's the technology solution. It is a tried solution. Okay, so this is just a picture of laser hardening. Now suppose you have, most of the time our tryout people are hand working to play with the bead height, because all they have is to play with the bead height. Either you make the bead tighter or you make it looser. Okay. So it involves hand work in any case, or it involves welding of the bead, which is no. We don't want to do that. Now if we can reduce dependence on bead, we can do so by resorting to nitrogen springs. If we are able to play with the pressures in nitrogen spring, whatever is achieved by bead grinding can be indirectly achieved by setting the pressure in the nitrogen spring, provided you are permitted to have different pressure in different nitrogen spring, which is normally not the practice. Normally the practice is that you have same pressure in all the nitrogen springs which are placed symmetrically, and you couple them with a ring main, so that if any single thing leaks, the whole thing leaks, otherwise die can break sometime. So from that fear, that is what has been the practice. But then nowadays technology has come that these things come with a built-in wireless smart sensor with a battery life of 5 years. Okay. So it can transmit the pressure reading through Wi-Fi, and you could have a software in your PLC or in your laptop, which is shown over there, where you can dynamically monitor that pressure should be what it should be, what it has been set to be, right? And then you can make tryout much easier by playing with the pressures rather than by doing handwork on the beads. Okay, that is one part. Now, how to make dies lighter? There are two pictures, upper pictures, the pair, and lower picture pair. They are essentially the same parts, door LH and door RH of a car, but you see the difference in size. Okay. So you can spot for yourself why the upper picture looks so much bigger, why the casting looks so much sturdier. Okay. Can it not be made lighter? Okay, lower die for once may not make a difference, but upper die does make a difference, because your press is lifting the upper die in every stroke, so you are wasting power. If you make the upper die lighter, you save on electricity, right? So that scope is definitely there. Now one more thing, what people are doing for making dies smaller and lighter is they are doing away with cutting steels. They have just on the edge, cutting edge, they apply welding, and then they hand finish the welding, so they get a hard edge. And all that is only required. You require a hard cutting edge, isn't it? You don't require a full brick, which should be hard, right? That's one idea which Japanese are doing, by the way. This picture, I mean, unofficially I can tell you it is from Honda. Honda is doing, and they are manufacturing what they are manufacturing is the best quality car, right? So those people can do, I mean, there's no harm in us doing it also. Okay. Now, another thing which is increasing the manual work is the base spotting and squaring of cutting steels, because dowels are not supposed to take the cutting force, nor and bolts have a clearance anyway. So you have to back up, the surface has to rest fully on the behind feature and on the base. So base spotting has to be done. So base spotting is being done. That requires a lot of handwork. For every steel insert, you have to do spotting, which is manual. Now, what some people are doing, like what Germans are doing, is that they are scanning the die and they are 3D printing the insert to suit the pocket, whatever is there. Okay. So that's the way they are doing it. Okay. So last point that I take to make the die little bit lighter. Sorry, I am exceeding the time, but I will just finish. See, a die cross section will look something like this. The problem is your standard, your company would have some standard for making these ribs, the rib thickness and the rib pitch. Usually there are company standards. Now these standards are unfortunately not based on properties of steel, they are based on property of thermocol. Because for making casting, thermocol pattern you have to make, and your thermocol pattern has to be sturdy enough to reach the foundry. If you make the ribs too thin, if you make the sections too thin from stress strain point of view in steel, your pattern will not last up to the foundry stage. So that is the situation in which we are, and what we could do is probably to have a 3D printing of pattern to make it strong wherever it is needed to be strong, and then possibly we can reduce the weight of casting by optimizing. We can have a pattern that will not break, or we can go for higher density thermocol, but in our context, to save some money, we buy cheaper thermocol which is lower density, and then we don't mind making the ribs thicker. So we save pennies, but we lose out on pounds. So that is the scenario. So I think I will end it here. It has been pleasure talking to you. There are some more slides, but then some other time probably. Okay. Thank you. You have been a wonderful, patient listener. Yeah. Oh yes.
Yes. Huge round of applause for Mr. Avinash Khare. Of course, the last session is challenging, and talking about challenges is equally challenging. Yeah. But the best part is we all enjoyed the session because he had put a little bit of humor in what he had to convey. Huge round of applause for the final speaker of the day. And now may I request President Tagma India, Mr. D.M. Shrigar sir, to please felicitate him. Huge round of applause for both the gentlemen. Calls for a perfect photo op. Thank you so much. We'll request sir to please stay on stage while I request Vice President Mr. Shanmuga Sundaram sir to please join us back on stage, and I can see all the lucky people in front of us, and we will